Hey everybody, I promised you that I'd make a little review screencast for the Unit 8 test, and this is exactly it. So let's dive right in, let's get started. So I'm going to work my way through the objectives that we had set for this unit, and let's start off by first making sure that we understand there's a couple things that we don't have to worry about. Suspensions and colloids, although they're interesting, we didn't really talk much about them, so we're just going to wipe those off of the objectives from the get-go. And where we started in this unit was fundamentally talking about different types of mixtures and really building off some prior knowledge about homogeneous and heterogeneous mixtures. So what's important to remember is in terms of the mixtures that we've discussed, we can have mixtures that involve various different things. If we can differentiate between those materials, then that is a heterogeneous mixture. And an example of a heterogeneous mixture is something like salad dressing or like chocolate chip cookies. That's a pretty decent example. My handwriting looks pretty awful here, but we'll make do. And on the other end of things, when we can actually easily differentiate one thing from, or when we can't differentiate one thing from another, that's homogeneous mixture. And this is really where we spent the bulk of our time, because these homogeneous mixtures are what we call solutions, right? Solutions, and these can be all kinds of things. We talked about air being a homogeneous solution because it's comprised of nitrogen gas primarily. There's water, CO2, there's some argon, there's carbon monoxide. There's all kinds of stuff mixed together in air, and you can't easily distinguish one thing from the other. And the bulk of what we dealt with, though, was liquid solutions, so something like salt water. The key idea is in a solution, you can't distinguish the substances, the pure substances, one from the other. It looks homogeneous. It looks uniform throughout. So that's the first thing. Check that off our list. Let's move on to the next thing. Describe the components of a solution. Well, for this one, I think it's going to be helpful if we actually look at a model. And if you look at what I've got right here, we've got a model showing some water molecules. And these water molecules don't have anything dissolved in them right now. So this is not an example of a solution just yet. But we can take something like table salt and add it. And when we add it, you'll notice that the substance dissolves. Now we have a mixture that's homogeneous because to our eyes we can't differentiate one part from the next. And notice that water orients a certain way around those ions. We'll get back to that in just a minute. So macroscopically, when we add something to make a solution, if it really is a solution, we can't tell one part from the other. Notice that in this solution that I've made salt in, there, you can't tell where the salt is and where the water is. It looks uniform. Now we know that it's here because you look at this table and it says that we've added some salt. And we could also add some sugar. And likewise, that sugar dissolves and the solution looks uniform to us. We can't tell where the sugar is. We can't tell where the salt is. But very much on the microscale, it is there. So if we want to take a microscale look at this, for adding salt, when it interacts, the salt dissociates and gets surrounded by water molecules. This is a picture of a solution. Okay? The one thing this picture is not showing is water. We could do the same thing and add some sucrose. And the sucrose dissolves in the solution. Okay? So now this is just a solution composed of soluble sugar, sucrose, and soluble sodium chloride. Now you may have noticed something that salt does that sucrose does not do. So let's take a look at this again. So notice that when I add salt, the sodium chloride breaks apart into ions. This process is called dissociation. Dissociation is where the positive cation and the negative anion get surrounded by water and pulled apart. This is partly a consequence of the behavior of an ionic substance. Now notice that when we do the same thing with sucrose, we don't get the same result. The thing that happens with sucrose is discrete molecules dissolve, but those molecules do not dissociate into ions. And that's an important distinguisher between sugar and salt. Okay? Remember sucrose, it's more of a covalent compound, okay, a polar covalent compound, but a covalent compound nonetheless. Sodium chloride is an ionic compound. And this brings us to a unique phenomena that we see. If I bring over my little conductivity tester and I reset it, notice that pure water does not conduct electricity. If we add an ionic compound, like salt, to it though, that solution conducts electricity. So that tells us that salts and other ionic compounds that are soluble in water behave as conductors. They behave as electrolytes. So we use that word electrolyte to describe substances that dissolve in water, making the water conduct electricity. Now notice if I remove the salt, the light bulb goes out. And if I replace the salt with sugar instead, we can test to see if sugar acts as an electrolyte. Notice I'm adding a bunch of sugar, but nothing's happening. That's because sugar is a non-electrolyte. Sugar does not break apart into charged particles in solution, so therefore there's no way for a current to be conducted. We would have to add salt in order to do that. And as soon as we add some salt, then we see the light bulb start to glow. So once again, salt is an example of an electrolyte because it allows a solution to conduct electricity. Sugar is an example of a non-electrolyte. And an easy way to tell, substances that are ionic and soluble in water are going to be electrolytes. Substances that are polar covalent or covalent compounds are not going to be electrolytes. So they would be non-electrolytes. Okay, so let's see how we're doing. Let's go back to our original table. So the components of a solution, I totally missed this. Remember that the components of any solution are always going to be those things that you must have to make a solution, which is going to be a solute and a solvent. So in the example that we originally started out with, we have a whole lot of water and just a little bit of salt. So the solvent is the substance present in the greater amount. In this case, the solvent would be water. And the solute is the substance that's dissolved in the solvent, in this case, sodium chloride. We could also have a situation where we added sugar to water. And in that case, the sugar would be the solute, and the water would still be the solvent. And notice that the water is slowly dissolving the sucrose by surrounding each molecule with water. Okay? All right, let's see where we are. So the components of a solution, solute, and solvent. How an aqueous solution forms, we've gone over that. That's where water surrounds those particles, and for an ionic compound, it breaks apart the ions into individual ions. And for a covalent or polar covalent compound, it just breaks that solid into discrete molecules. Now, we've talked a couple of ways in lab about how we can separate a mixture. And one way in particular that we did that was through a process that's technically known as distillation. But let me just describe it in context for us. If you remember the separating mixtures lab, most groups had a scenario where you had a solution that contained KCl and water. And what we did to separate the two is we put it under a hot plate. And I'm just going to make a little flame here to symbolize that. And what you noticed was the water evaporated. And it evaporated because it has a lower boiling point than the salt did. So over time, after some time had passed, right? So after some amount of time, we were left with a beaker where all of the water had been driven off and gone into the atmosphere. And what we were left with was our solid KCl. So that's a process of distillation. Typically it's used with two liquids, but in this case we're just taking advantage of differences in physical properties. In this case, they're differences in boiling points. Another example of how we've separated solutions, components of a solution, has been using something called chromatography. Now it's probably an unfamiliar word to you, but when I describe it, you'll know what I'm talking about. There was one part of our polar substances lab where we had two different inks. If you remember, one of them was the semicircle and the other was another semicircle, and then we added things like water to it. And what you noticed is in some cases that ink would start to bleed. and in other cases, the ink would do nothing. So we can use a solvent to separate certain components from a mixture, and this is called chromatography. All right. So the next thing for us, identify solutes as polar, nonpolar, or ionic, provided their structure and formula. Now there's some additional information that we'll give you with this, but fundamentally what you need to understand is we spent some time thinking about what this statement means, this statement of likes, dissolve, likes. And fundamentally it boils down to this. If you've got a polar solvent, it will dissolve things that are very similar to it. And remember, polar solvents have partial charges. So that means it will be able to dissolve other things that also have partial charges. Blah. So that means it will dissolve polar compounds, and it will likely dissolve ionic compounds. And water is our primary example of a polar solvent. Okay, so if something dissolves in water, it's very likely to be polar. And remember, we can differentiate very easily between polar and ionic because an ionic compound is comprised of a metal and a nonmetal. Okay. Now, on the opposite hand, if we look at something that is nonpolar, so a nonpolar solvent will only dissolve other things that are nonpolar. So we can use that to our advantage. If I tell you that something dissolves in water, we know that it's either polar or ionic, so we just need to think about whether or not the substance has a metal and a nonmetal, making it ionic. If a substance does not dissolve in water, then that lets us believe that the substance is probably predominantly nonpolar in its nature. All right, next thing, identifying factors that affect the rate of a substance dissolving. This one's a pretty straightforward one because if you think about ways that you could get something to dissolve faster, it goes pretty quickly. So things that can affect the rate of a substance dissolving, there's a few primary ones. Number one, stirring. Stirring causes the solute and solvent to interact more frequently, making the substance dissolve at a faster rate. Another thing that we could do is change the particle size. For example, if you take powdered sugar, it will dissolve in water much more rapidly than a sugar cube will. That's because the size of the particle is small, which means water can easily surround it and dissolve it. Okay? The other thing that we can do to influence the rate of something dissolving is to use temperature. For most solids, as you increase the temperature, the rate increases as well. All right, next, let's look at the difference between saturated, supersaturated, and unsaturated solutions. And for this one, we're going to go back to another model. So first, let's make a solution. I'm just going to make a solution of salt water. And notice my salt water, now I've got a solution because it's all dissolved. This substance, this solution, is relatively dilute right now. There's not a whole lot of ions per unit volume. We can increase the concentration by adding more salt. And as we add more salt, we have to wait for that salt to dissolve. Now it's still dissolving. So our solution has not yet reached saturation. Okay, so right now the solution is unsaturated because more salt could dissolve. And the way to test it, we add a little bit more. And that additional amount we added still dissolves. Now the point where we reach saturation is the point where no more additional salt will dissolve in our solution. And the way to really know that visually is we add some more salt and we wait till the point where not all of the salt dissolves. So notice that in this case, there's a pile of undissolved salt floating around in my solution. That means the resulting solution that's around that pile of salt is saturated. It can't hold any more salt. Now, if I was to heat this solution up, that would make the additional salt dissolve. And at that point, what that would mean is if I cooled it carefully, back down to this original temperature and none of the salt crystallized out, that would be the scenario where we had a supersaturated solution. Normally, supersaturated solutions are quite unstable, and what is going to be more in our points of discussion are going to be whether or not we know if a solution is unsaturated or saturated. And you can tell that easily by a little experiment like this, or by using and interpreting a solubility curve. All right, now we've talked about how ionic solutes behave differently from covalent solutes in aqueous solutions. Just remember, if you forget me talking about this earlier in the screencast, ionic solutes dissociate into ions. Covalent solutes dissolve to form molecules in solution. Ionic solutes are electrolytes, which means they allow electricity to be conducted through a solution. Covalent solutes are non-electrolytes, which means even if they dissolve in water, that resulting solution does not conduct electricity. Okay, moving on to acids and bases. So how do we identify something as being an acid or a base? Now for our definition of an acid, we're going to take a very simple definition of an acid. An acid is anything that when it dissolves in water gives us hydrogen ions. And the dead giveaway for us is the acid starts with a hydrogen. This particle that it dissociates into that we consider the acid particle is the hydrogen ion. Sometimes it's referred to as a proton, but we're just going to call it our acid particle, and its name is the hydrogen ion. Okay? Now for a base, the way to tell that we're dealing with a base is most often a base contains hydroxide. And when that dissolves in water, it gives us a metal ion and a polyatomic ion called the hydroxide ion. So whereas the acid particle is H+, the base particle is OH-. And remember that that is called the hydroxide ion. Okay, so fundamentally, the way to tell a difference, acids start with H, bases have OH in them. All right, next piece, using pH to determine if something is acidic or basic. The fundamental thing to remember about pH is a measure of a particular particle, the acid particle, the hydrogen ion. And our scale that we use goes from 0 to 14. We define 7 as neutral. If you have a pH value that's between 7 and 0, that's considered acidic. And that just means we have lots of H+ ions in solution. And if our pH is above 7, that means the solution is basic, which means fundamentally we have lots of hydroxide ions in solution. So we can use indicators to give us a general gauge as to whether our substances are acidic or basic. And you should review your lab that we did on indicators, that very first part of the acids, bases, and indicators lab activity, to be familiar with how red litmus paper behaves, blue litmus paper, that type of thing. Okay, almost done. And the final piece is writing balanced equations for the reaction between acid and base. And there's a general format that we can use that goes back to when we first learned about a type of reaction called a double replacement reaction. If you recall, a double replacement reaction follows a pattern. AB plus CD goes to AD plus CB. Now, the key change for us now is dealing with an acid and base. An acid plus a base always gives us predictable products. And those products are a salt and water. So knowing that, we can do some examples. And a typical acid, like the one we used in lab, hydrochloric acid, will react with a typical base, sodium hydroxide, and we know it makes water. To figure out the rest of the bit, well, just figure out what's left other than water. So we've got the chloride ion and the sodium ion. So that means our other product, in this case, would be sodium chloride and water. And the final step whenever you're writing an equation like this is to make sure that it's balanced. Now in this example, the equation's already balanced, so let's look at one where we'll have to change some coefficients. So let's take sulfuric acid, H2SO4, and react it with NaOH. So think for a second, what do you think the salt's going to be? I mean, we know water's going to be formed. So take a minute and think about what you think the salt would be. Hopefully you recognize that it's going to be between the sodium ion and sulfate. But we have to remember that sulfate has a -2 charge. Sodium has a +1 charge. That means we need 2 sodiums with 1 sulfate. So this equation in purple is our unbalanced chemical equation. Now we might have to change some coefficients. Let's do some quick counting. If you notice, we have 1 sodium ion here. Over here we have 2. I have to put a coefficient of 2 in front of sodium. Now let's look at the rest of this. So I've got 2 hydrogens here, plus another 2 hydrogens here. That's a total of 4 hydrogens. Over here I only have 2 hydrogens. So I'm going to add a coefficient here. Now let's just start from the beginning and see if we've gotten everything balanced properly. So we have 4 hydrogens on this side, and on the product side, 2 times 2 gives us 4 hydrogens. So hydrogen is balanced. 1 sulfur, 1 sulfur. 4 oxygens plus 2 more oxygens, so that's 6 oxygens on the reactant side. 4 oxygens here, plus an additional 2, that's 6 oxygens on the product side, so oxygen's balanced. 2 sodium atoms, 2 sodiums, and we're good to go. This equation is balanced. So I think that about covers it for our Solutions Review screencast. The only other things you might want to go over is the homework assignments dealing with solubility charts and interpreting solubility curves. But hopefully this is a good start for you as you review. Hope you guys have a good afternoon. See you later.